Okay, I wrote on the board. You guys are going to have your limits exam on Thursday, February 16th. I'll give you a review assignment to work through to help get you ready. We'll also make sure that we go through that quiz that you guys wrote prior to the test. So test Thursday. Pardon me? No. No, no more quiz.
Who needs quizzes when you can just ace the exam? What? Oh yeah, I think you're doing a lab today.
Okay, so lesson 8. We're going to start seeing different applications of finding limits. One of them we've already seen is if you wanted to find the equation of a tangent line to a curve at a certain point, we can use one of those limit formulas to get the slope of the tangent and then write the equation. So we'll start to look at some other applications of limits. If a vehicle is driven 270 kilometers over a 3-hour period, the average velocity can be determined by taking the distance over time, and because it's kilometers on top and hours on the bottom, you get your average velocity in kilometers per hour. However, this does not define the instantaneous velocity at a specific moment in time. This instantaneous velocity can be found using limits. If y equals f at x represents the equation of an object in motion, then the instantaneous velocity at a time t equals a will be the slope of the tangent line to y equals f at x. So that's one of the applications of the slope of the tangent line. It'll give you the instantaneous rate of change of one object with respect to time. Okay? So we're going to use those same formulas that we looked at last week to take the limit. So the first example, a ball is dropped from a height of 500 meters. Find the instantaneous velocity after 5 seconds. And we need to use the fact that the distance that an object falls after t seconds is defined by s equals f at t equals 4.9 t squared. So we've seen that the instantaneous rate of change can be found by finding the slope of the tangent at that point, which we can find using one of those two limit formulas. It doesn't matter which one we use. So we are finding the slope of the tangent line, and in this case here, it'll be the limit as t approaches 5 of f at t minus f at a all over t minus a. So that's that formula that we saw last week. So this will be the limit as t approaches 5. F at t is the function in terms of t minus f at 5. So that'll be 4.9 times 5 squared. Right? The formula is 4.9 t squared. And so the second part on top, the second term, is the value of the function when t equals 5, all over t minus 5. So again, 5 is a non-permissive value, which we've seen is normally the case. So we need to do something to get rid of that t minus 5 on the bottom. Now, you might think that the first thing you would do is square the 5 and multiply by 4.9, and that you could do, but it's actually going to be easier if we don't do that, but we just start factoring the top, because we can start by taking out a common factor of 4.9 on top, which will give us t squared minus 5 squared, or t squared minus 25 if we want, and that is a difference of squares. You can leave it in the formulas right now, and it's a difference of squares. Or you can say 5 squared is 25, it's still difference of squares, it's still going to give us the same factors. So this will be the limit as t approaches 5 of 4.9 times t plus 5, t minus 5. And so now the t minus 5s will cancel. And we've gotten rid of that factor of t minus 5 on the bottom. So now we can evaluate this when t equals 5. So this will be 4.9 times 5 plus 5, which is 10, or 49, and that would be in meters per second. So again, one of the applications of the slope of a tangent line is the instantaneous rate of change. In this case, it's the instantaneous rate of change of meters with respect to the time in seconds, which is the velocity. That's the instantaneous velocity at 5 seconds. That object is falling, and at 5 seconds after it's been dropped, it'll be traveling at 49 meters per second. Instantaneous rate of change. So number 2, the displacement in meters of a particle moving in a straight line is defined by s equals t squared plus 2t, where t is the time in seconds. Determine the instantaneous velocity after 3 seconds. So again, we can do this by finding the slope of the tangent line to the curve t squared plus 2t at the moment when t equals 3. So if we use that first limit formula again, because you can use either one, it doesn't matter. In this case, it'll be as t approaches 3 of f at t, which is t squared plus 2t, minus f at a, which in this case would be 3 squared plus 2 times 3, all over t minus 3. So right now 3 is a non-permissive value, so we need to do something to this function on top so we can get rid of the t minus 3 on the bottom. If you find the constant term by going 3 squared, which is 9, plus 2 times 3 is 6, 9 plus 6 is 15. And then we can factor. It'll be t plus 5, t minus 3, and the t minus 3's cancel. We've now gotten rid of that factor of t minus 3 on the bottom, and we can evaluate the limit when t is 3. 3 plus 5 is 8, and that would be in meters per second. We're told that displacement is in meters and the time is in seconds, so 3 seconds after that object has started to move along that straight line, its instantaneous rate of change, or the velocity, at that moment will be 8 meters per second. Okay? So example 3 says a thermometer is taken from a room where the temperature is 20 degrees Celsius to the outdoors where the temperature is 5 degrees Celsius. The temperature readings were taken every 30 seconds as shown in the table. You're going where? Okay. So every 30 seconds, the readings are taking off the thermometer. Now the first part of this sign asks us to find the average rate of change of temperature with respect to time over the following time intervals. And at the start of this lesson, we saw how you can take the average rate of change, you take the total distance traveled in that time period, and divide by the time period. And basically what you're doing is you're using the slope formula. Okay, that first example went from 0, 0 to I think 270, 3, or 3, 270, I should say. And so if you use the slope formula, y2 minus y1 would be 270 minus 0 on top over 3 minus 0 on the bottom. That gave us our 270 over 3, or 90 kilometers per hour. So basically you're using the slope formula if you want to find the average rate of change between two time intervals. So in part A, it wants us to find the average rate of change, and in part 1, between t equals 2 and 4 seconds. So again, we're just using the slope formula, which is y2 minus y1 over x2 minus x1. So between 2 and 4, so our y2 value will be the temperature at 4 minutes, which is 5.7, minus y1 will be the temperature at 2 seconds, because we're finding the average rate of change between t is greater than or equal to 2, less than or equal to 4. And at 2 seconds, the temperature was 8.3 degrees, over x2 minus x1, which would be the difference in the two times, 4 minus 2. So 5.7 take out 8.3 is negative 2.6 over 2, which is negative 1.3 degrees per minute. So that's the average rate of change between 2 and 4 minutes. Right? It came from inside where the temperature was 20 degrees to outside where the temperature was 5 degrees. So the temperature in the thermometer will be decreasing. That's why we get a negative value here. Now, so that was part 1. Part 2, between 2 and 3.5. So again, m, the slope, will be y2 minus y1. y2 will be the temperature at 3.5, which is 6, minus the temperature at 2, which is 8.3. So essentially, we're just sliding the second arrow over to 3.5 seconds. And that'll be divided by the time, the two times, which is 3.5 and 2. So 6 take away 8.3 is negative 2.3 over 1.5, and that gives us negative 1.5 degrees per minute. A little bit different than it was for interval number 1. And then finally, part 3, if we want to find the average rate between 2 and 2.5 seconds, so again, we'll move this arrow over here, and y2 minus y1 will be the temperatures, the difference in the temperatures, 7.2 minus 8.3 over x2 minus x1, which is the difference in the times. So that'll be negative 1.1 over 0.5, which is negative 2.2 degrees per minute. So what we've done here is, this is no different than we found the slopes of those secant lines. As the second point got closer and closer to the point of tangent C, the slopes of those secant lines approached the slope of the tangent line. We're doing exactly the same thing here. We're finding the slope of the secant lines as t gets closer and closer to 2 minutes. Right? We went from 4 minutes down to 3 minutes, down to 3.5, I should say, down to 2.5. We're getting closer and closer to 2 minutes. So these rates of change, the average change in temperature, would be approaching the instantaneous rate of change, the instantaneous change of temperature at 2 minutes. So on the next page, it says sketch the graph of temperature as a function of time and estimate the instantaneous rate of change with respect to time when t equals 2 minutes. So if we're going to sketch this graph, we will have time in seconds along the bottom. That's what t is. I'm sorry, not seconds, minutes. That should be minutes. And along the side, we have the temperature in degrees Celsius. So I'm going to use a scale along the bottom of a half, which means the second vertical line will be 1 minute, the fourth vertical line will be 2 minutes, and so on. And along the side, the room that the thermometer came from was 20 degrees, so we just have to choose a scale that will allow us to have 20 degrees somewhere on here. So I think if I go 1, 2, 3, 4, 5, 6, 7, I think it's going to work if I use a scale of 1, but I'll just put down every second degree. So 2, 4, 6, 8, 10, 12, 14, 16. Actually, it's not going to work. I'm going to run out of room here, but that's okay. We'll just kind of guesstimate where that 20 degrees would be. Somewhere there. Okay, and if you look back, we're not going to put all the points on here, but we can start with the point 0, 20. Let's do 1, 12. Let's do 2, 8.3. Let's do 3, 6.5. 4, 5.7. And 5, 5.3. Right? And we want to use this graph to estimate the instantaneous rate of change at the moment when t is 2 minutes. So if we look on our graph at t equals 2 minutes, that's approximately right there. Right? We have that point on our graph, but we want to find the slope of the tangent at that point. That gives us the instantaneous rate of change, the slope of the tangent at that point. And this is just going to be an estimate. I mean, obviously my graph is not perfect. But we need to find 2 points that are on this line and then use the slope formula. So 2 points that are on this line. So just looking at it, and again, it's not perfect, but let's say we take that point right there, which is the point 4.5, approximately 4.5, comma 3. So 1 point will be 4.5, comma 3. The other point, again, it can try our best to try and choose a point that looks like it's on that line. So maybe we'll use that point right there, which looks like it's at about 1.25, comma 10. Again, this is just a guess, right? It's an estimate. So m, the slope, is found by y2 minus y1 over x2 minus x1. Remember, we're finding the slope because the slope of the tangent, we now know one of the applications of that, it gives you the instantaneous rate of change of one object with respect to time. So here it'll be 10 take away 5.3 over 1.25 take away 4. So 10 take away 5.3 would be 4.7. And on the bottom, 1.25 take away 4 would be negative 2.75. And then we'll use our calculator to get that. So it's approximately negative 1.7 degrees per minute. Approximately. And again, this is just an estimate. We don't have an equation, so we can't calculate the instantaneous rate of change. It's just an estimate. Okay? Now, you can use your calculator to get the equation of this. Okay? You can put those points into your calculator, and your calculator will spit out the equation, but that's not part of this curriculum. It's just a regression formula. So I'm not going to show you how to do that because you don't need to know how to do that. Never be tested on this. Right? But in order to find the instantaneous rate of change, you'd need that formula, that curve. Okay? The next one, a spherical balloon is being inflated. Find the rate of change of volume with respect to radius when the radius is 10 centimeters. So as the balloon is inflating, you can talk about the change in volume with respect to time, but now we see that you could also, in this case, find the rate of change of volume with respect to the radius. As the balloon is being inflated, the radius is increasing, and the volume then is increasing as well. So we're going to find the rate of change of volume with respect to radius, and the reason it has to be that way is because the formula for volume is in terms of radius. The formula for volume of a sphere, which is a ball, is 4/3 pi r cubed. So on the test, if you need any of these formulas, they'll be given to you. You don't have to memorize them. But because the formula for volume of a sphere is based on r, the radius, we have to find the rate of change of volume with respect to radius. We've got no other choice. So again, this can be done by finding the limit. In this case, as r approaches 10 centimeters of v at r, which would be 4/3 pi r cubed, minus v at 10, so it would be 4/3 times pi times 10 cubed, all over r minus 10. 10 is a non-permissive value, so we need to do something to get rid of that r minus 10 on the bottom. And that something, again, would be factoring. So the first thing I would do is I would take out a common factor of 4/3 pi on top. Common factor of 4/3 pi leaves us with r cubed minus, now again, you might want to cube the 10 to get 1,000, but I'm going to leave it as 10 cubed because now I can factor r cubed take away 10 cubed as a difference of cubes. The first term is a perfect cube and the second term is as well. There's a minus sign in between. So we'll factor that as a difference of cubes. So it'll be 4/3 pi. So the cube root of r cubed is r. The cube root of 10 cubed is 10. That gives us the terms of the binomial. To get the terms of the trinomial, square the r, multiply the 10 and the r together, square the 10. And the sign pattern for difference of cubes is minus plus plus. But because that second factor on top is r minus 10, they will cancel. We've now gotten rid of our factor of r minus 10 on the bottom. That gave us a non-permissible value of 10. We can now evaluate this when r equals 10. So it'll be 4/3 pi times 10 squared, which is 100, plus 10 times 10, which is another 100, plus another 100. So that'll be 4/3 pi times 300. You can divide top and bottom by 3. 300 divided by 3 is 100. And if you multiply out what we have left, and I'm going to leave it in as an exact value, it'll be 4 times 100, which is 400 pi. And this is the rate of change of volume, which will be in centimeters cubed per centimeter of radius. So as the balloon is being inflated, at the moment when the radius is 10 centimeters, the volume is increasing instantaneously at a rate of 400 pi centimeters cubed per centimeter. If you went a little bit past 10 centimeter radius, that would change. The instantaneous rate of change would be different. And if you went something a little bit less than 10, same thing would happen. The instantaneous rate of change would be different. So again, this is one of the applications of those limit formulas. The slope of the tangent tells us the instantaneous rate of change. In this case, an object is shot into the air using a slingshot and follows a path defined by s at t equals negative 4.9 t squared plus 21.5 t. Find the instantaneous velocity after 3 seconds. So the instantaneous rate of change, again, is found by taking that limit. So I'll have the limit in this case as t approaches 3 of f at t minus f at 3. So that's negative 4.9 times 3 squared plus 21.5 times 3. So let's use our calculator to find out what that constant term is. Negative 4.9 times 9, that's 3 squared, plus 21.5 times 3. I did. It would be, which gives us 20.4 as a constant. Positive 20.4 because there's a negative in front of that bracket. It'll be minus 20.4 for a constant term. And I also forgot to write t minus 3 on the bottom. So this is the limit as t approaches 3 at negative 4.9 t squared plus 21.5 t minus 20.4. So we do have a slight problem here because you can't factor the numerator. Okay, you could take out a common factor of negative 4.9. So let's see what happens when we do that. If you go 21.5 divided by negative 4.9, you see what you get for that middle term. Okay, and same thing with 20.4 divided by, and I guess it is negative 20.4, but it doesn't really matter whether it's positive or negative. When you divide them out, you get those decimals. So taking out a common factor of negative 4.9 would not allow us to factor the trinomial. But we need some way to get rid of that t minus 3. And that some way in this case would be to actually divide them. Divide the quadratic on top by t minus 3 on the bottom using synthetic division. Did that in 30-1, right? So instead of dividing by t minus 3, we normally change it to t plus 3 so that we could add as we're going along using synthetic division. T plus 3 into negative 4.9 t squared plus 21.5 t minus 20.4. So negative 4.9 times 3 is negative 14.7, so that's what goes up here. And then we add. Right? We're using synthetic division here. So the negative 14.7 plus 21.5 is 6.8, positive. And then that 6.8 is multiplied by the 3 in front, which gives us positive 20.4. And And when you add those, you get your remainder of 0. And that's the only reason why this is going to work, because if we got a remainder of something else, we would not be able to evaluate this limit algebraically. We couldn't. So, back up to the equation. This will now be the limit as t approaches 3. When you divided that out, you got negative 4.9t plus 6.8. Right? You divided a quadratic, a t squared, by a t. That gives you a degree 1 answer. That's why it's negative 4.9t plus 6.8. So by dividing out, you've gotten rid of that denominator. You can now evaluate this when t is 3. So it's negative 4.9 times 3 plus 6.8, which is negative 7.9 meters per second. So there's the instantaneous rate of change of velocity at the moment when it is after 3 seconds. So again, the fact that it's negative means that it's slowing down, right? The slingshot shoots that object up into the air, gravity starts acting on it immediately, and it starts to decelerate to the point where that would reach a maximum point, and then the velocity would be 0 at that moment, and then it would start to fall, and then the velocity would be increasing. The fact that it's negative tells us that this object has not reached the maximum point yet. It's slowing down because of gravity. Okay, so again, what we've seen, one of the applications of the slope of a tangent is finding the instantaneous rate of change of an object. And normally it's in terms of time, but we saw in the case of the balloon, it was in terms of r, the radius. As the radius of the balloon changed, the volume changed. And it's all tied to the original formula. What is the independent variable in that formula? That's what the velocity is changing with respect to. So for practice, you can work on those questions. I will post the solution to Google Classroom so you can check your work. And again, remember, Thursday, February 16th, you guys are going to write your quiz on limits. So tomorrow I will give you your review assignment so you can start working on it. And we'll also be going through that limits quiz so you can see what you did wrong on that. Okay?